Hi, everyone. I'm Matt Engelhardt from Duke University, and I'd like to give you a quick overview of our work, neural conditional event time models for prediction of diagnoses and other health events. Event time models, you might know them as survival analysis models, are common in medicine to predict patients' risk of medical events over time. These models can learn from censored events where the event time is known only to be above or below a certain value. This is critical not just because we get more data, but also because we avoid bias. If we get rid of patients with inadequate follow-up, for example, we might even lock in health disparities with our model. But event time models have a key limitation. They assume the event always occurs eventually. If we're predicting survival, this is fine, we all die, but not everybody has a heart attack, not everybody's diagnosed with autism, and so on. And for events that don't always occur, the event time model doesn't understand the difference between event occurrence and event timing. In many cases, what we really care about is event occurrence, a patient's lifetime diagnosis risk, for instance, whereas diagnosis timing may have more to do with the person's circumstances, say their access to care, than their health. We might also want to analyze factors affecting timing separately from those affecting lifetime risk, but event time models won't help us do that. Our solution is the conditional event time model. Like the standard model, we start with patients, associated times, and an indicator telling us whether it's an event time or a censoring time. But in the new framework, we're interested in hidden binary variables, one for each event type, that specify whether the event occurs ever in a given individual. We model finite event occurrence with a binary stochastic layer, then use a gradient estimator like Gumbel softmax to backpropagate across it. But the key here is the likelihood. We make sure it's numerically stable for large data sets, but we also have to penalize the model when it predicts that events won't occur in cases where they are observed. Censoring times are still critical. If a patient's quickly lost to follow-up, for example, there's a fair chance they were diagnosed even though we can't see it, but if they're followed for 70 years, let's say, a diagnosis isn't very likely. Our synthetic results show us that all this actually works. First, we give a binary classifier perfect information about event occurrence. There's no censoring, nothing hidden from view, and as expected, it makes near perfect predictions. But once we introduce censoring, the binary classifier starts predicting whether events will be observed rather than whether they'll take place. The standard event time model also performs poorly, but for a different reason. It's making similar predictions for patients at low risk and those with high event times. But our model still predicts event occurrence effectively. Not as effectively as we could with perfect information, but much better than other options for censored data. But what about real data? We looked at prediction of lab orders in Mimic3, ones that are clinically meaningful and not routinely collected, and it posts to mental health subreddits. Most people don't post there, so again, using our model makes sense. And in both cases, we see the same effect. We're predicting event occurrence more effectively, and on top of that, our timing predictions are improved because the model distinguishes event timing from event occurrence. So if you're predicting survival, stick with survival analysis, but if you're predicting medical events that don't happen to everyone, we think CET is a better choice. Thanks for listening. We'd love to meet you to discuss this work and yours.